In this video demonstration, we'll look at functional design validation inside Solid Edge using a product called Dynamic Designer. We'll look at what Dynamic Designer is, the benefits it provides, how it differs from some of the assembly motion capability currently inside of Solid Edge. We'll look at the data that it can provide, and we'll also look at how it's a strong prerequisite tool for providing the FEA boundary load conditions. Finally, we'll follow it up by a demonstration. Dynamic Designer is a tool for helping understand the functional performance of your Solid Edge design so that your design can be validated early before any physical testing or problems are encountered. It helps answer the question about your design: will it work and will it function? And it also helps provide the boundary conditions for helping you understand, will it break? Some of the benefits of Dynamic Designer: the time and money associated with fixes on the floor and pre-production changes can be significant, but identifying problems early in the design cycle can translate to a huge cost savings. The time and money associated with physical testing can also be tremendous, but reducing and/or eliminating physical testing and prototypes also can translate to a huge cost savings. Field failures and warranty claims can incur a lot of unexpected cost, and too late is simulation looked at as a solution long after failures have already occurred in the field. And finally, if less time is spent trying to fix problems that were not identified early through simulation techniques, then more time can be spent developing better quality products and helping you gain a competitive advantage against your competitors. Dynamic Designer is more than just CAD assembly motion. Solid Edge can do a good job at showing you movements based on kinematic constraints and also some dynamic interference detection, but that's not taking into consideration mass, inertia, and gravity. Dynamic Designer can consider those movements utilizing mass and inertia effects. Interference in Solid Edge can be limited to some of the assembly movements, but sometimes that movement may be based on more complex movements that involve the effects of gravity and speed, and so Dynamic Designer can capture that. Finally, Solid Edge doesn't allow you to determine the physical data behind those movements. Dynamic Designer is providing the true physics of the motion and the model, things like displacement, velocity, acceleration, and force. Some of the things that can be output from Dynamic Designer are your basic physics type information, as well as trajectory curves, graphical vectors. Simulate things like ball screws, linkages, gears, and cams. Dynamic Designer also provides the FEA boundary conditions. You can automatically transfer loads from a Dynamic Designer simulation to a Solid Edge simulation, helping you understand the correct load type, value, and direction. Dynamic Designer is a great reverse engineering tool for understanding what cam profiles need to look like, or sizing motors and actuators. Dynamic Designer has an API interface, which stands for Application Programmer's Interface, and allows you to customize the program to fit your simulation routines. We can also output AVI videos, so you can capture a video of your animation, great for design reviews and sales presentations. Dynamic Designer is a prerequisite to FEA. Dynamic loads, how are they typically calculated for an FEA model? Physical testing, hand calculations, or best guess. This can be time-consuming and inaccurate. Some of the consequences of an inaccurate FEA setup: you can underestimate the load magnitudes, improperly assume the types of loads and the direction, and neglect loads that could be a direct function of the dynamics of the mechanism, where acceleration loads may be significant. Dynamic Designer can automatically transfer these loads as boundary conditions to a Solid Edge simulation. The advantage of being embedded inside of Solid Edge: Dynamic Designer can automatically create the kinematic joints based off of the Solid Edge assembly relationships. Mass and inertia properties transfer automatically into Dynamic Designer. And design change recognition is easy. So to go back and forth and understand the change of performance due to a design change is very easy. and transfer forces and moments to a solid edge simulation for finite element analysis. Some of the applications of Dynamic Designer: gear mechanisms, cams, linkages, motors and actuators, system compliance, and visualization and animation, such as interference detection, cycle times, and sequencing. Who is using Dynamic Designer? Customers ranging from medical, aerospace, rail, and automotive. Here's a simple demonstration of Dynamic Designer. We'll take a look at this machine here. In particular, we'll look at a subset of this machine, and we'll take a look at a few different objectives. We'll look at determining the motor input torque on this shaft. We'll look at determining some of the bearing loads for these radial bearings. And we'll also look at transferring part loads for this red link here into a solid edge simulation in preparation for an FEA. So let's go ahead and get started. We'll toggle over to Dynamic Designer, where I have a model ready to simulate. It is that subsystem of that larger assembly that we looked at. To launch Dynamic Designer, we can click on Tools, and then we can click on the motion icon. And when we do that, that will create a mechanism called Motion Model. And notice our browser changed over here. The first thing we do is we begin by defining a mechanism. So we can right-click on Motion Model and choose New Mechanism. We can give this any particular name if we wish. I'll leave the default. And once we do this, we get a message here. What this message is doing, it's saying that if a part in the solid edge assembly has more than 0 degrees of freedom, Dynamic Designer can optionally consider that part as moving, and if it has 0 degrees of freedom, it can consider it as grounded. I'll go ahead and I'll choose no to this because I'd like to show you the alternative way to defining these parts. You can see here in the browser that we now have several parts populating the assembly components node, and then we have some other nodes here: moving parts, ground parts. We have some different constraint options, springs, dampers, forces, and then we have the post-processing area for looking at the data. And then finally down at the bottom, if we include parts in a solid edge simulation study, or when we create a solid edge simulation study, those parts will show up here for availability and transferring the motion loads. So we'll go ahead and we'll start by defining our ground parts. I'll go ahead and I'll select all these parts here. And selecting these parts is just like selecting files in Windows Explorer by holding down the Shift and Control keys. I'll select these rails, and then I'll right-click and choose Ground Part. And then I'll select the coupler arm, and this part, and these 4 parts here. And we can, again, either right-click and say Moving Part in this case, or we can click, hold, and drag and drop. We get a message here notifying us that the assembly relationships were mapped into kinematic constraints. And we can see on the screen here that we have these different icon representations of those constraints. If we look over on the joints node, we can see those constraints listed. These constraint names can be changed if preferred. The first thing we'll do is run the simulation with gravity just to see what happens. So we'll come down to the bottom of the browser and we'll click on this calculator button. Okay, and the simulation is complete. And we can see we have a little bit of work yet to do. Okay, and I purposely left out some of the constraints because I'd like to show you how we would go about creating them in Dynamic Designer. So let's delete the simulation results by clicking again the button we launched the simulation with. And then the first thing we'll do here is change the direction of gravity. Using the orientation indicator over here, I'll set gravity to act in the negative y direction. Next, I noticed there was a constraint missing for this slide. So let's go ahead and let's add a constraint in here. Dynamic Designer has its own set of joints or constraints. If we right-click on joints, we have several different types of joints that we can add. It's important here to note that the functionality is unidirectional. By that I mean if we create a joint in Dynamic Designer, it does not create the assembly constraint in Solid Edge. But if I create the assembly constraint in Solid Edge, I can optionally bring that into Dynamic Designer. I'll go ahead and I'll create a translational joint. And I start by selecting the first component, which is the slide. The second component, I'd like to attach it to the background. The location, I'll use the midpoint of this line. And for the direction, I'll select this face to make the orientation for the z-axis normal to that face. So you can see that joint icon representation. The nice thing about Dynamic Designer is it is associating its references here for location and direction with the features of the parts. If the part features are changed, the Dynamic Designer definition will remain. Let's choose OK. And we'll go ahead now and we'll run the simulation again. Okay, and we see that we have one thing missing here. That pin should be constrained to that roller. And I forgot to do a couple things here. I forgot to attach these parts. Simple enough to do. This coupler subassembly needs to be attached to that shaft. We'll right click, choose Attach To, select the shaft. Here's that warning or that information message again. Okay, I'm also going to attach the roller to the top pin, and then the roller block I'll attach to the slide, and it automatically creates rigid constraints between those two, and it is including the mass and inertia properties of those parts, so I'm not leaving anything out. So let's run the simulation again. That looks much better. This would in fact oscillate perpetually because I don't have any friction defined in this model. So I have a theoretically perfect mechanism here that would achieve perpetual motion. So let's go ahead and let's start by taking away the tangent constraint between the roller and the block. We can see we have this tangent relationship that was brought over from the Solid Edge assembly. So I'll simply delete it, or whoops, let's first delete our simulation results. I'll either delete it or suppress it. So I'll just go ahead and choose to delete it. I don't need it anymore. And what we're going to do instead is we're going to replace it with a contact. The benefit of using these contacts is that the contact can be intermittent. So if the part has clearance in here and we end up with some sort of chatter effect due to high speeds, we'll be able to capture that in a force plot for the contact. If I click on the Contact tab, here's where I can turn friction on or off. And typically what we do in a model when designing it and designing a simulation model is crawl, walk, run. Start with a simple model, leave out the complex details until the end. So for now we'll turn friction off on that roller. I also have the ability to add materials in here. So currently it's going to use steel on steel as the material properties. I can override these and I can select from a material that I may have defined earlier, such as DST steel. Next, we'll go ahead and we'll add a motor to turn the shaft here. So let's spin this around. And I have a joint that was brought over from the Solid Edge assembly relationships, but the orientation is not entirely correct. So what I'll do is I'll simply suppress or delete that joint, and I'll define a Dynamic Designer joint here. So I'll right click on joints, and this time I'm going to add what's called an inline joint primitive. The advantage of having joint primitives is because in any rigid body simulation software we can come across things called redundant constraints, and these primitive type joints help you construct a model so that you don't have redundant constraints. I'll choose a location and a direction to orient. So basically this is a spherical joint that's allowed to translate along a straight line. However, the reason it will not translate and slide out of the bearings is because it's also held down here by a ball joint. So ultimately the degrees of freedom of the shaft are a single rotational degree of freedom. So what we'll do now is we'll apply a motion on the joint we just created. So we can right click on that inline joint, and notice over here in the graphics window it shows that that joint is highlighted. We'll choose Properties, click on the Motion tab, and here we have the ability to control any of the degrees of freedom of that joint. And since it's a 4 degree of freedom joint, I can control simultaneously, if I wish, all of these degrees of freedom. I'm only interested in controlling the rotational axis of that joint to represent a motor. Now I'll change the motion type to velocity, and I'll leave this at 360 degrees per second. It's worth noting in here that there are other function types we can use, such as step function, sinusoidal, or harmonic. We could also import data from a spreadsheet where we can correlate physical and virtual models. And we can also build a mathematical expression of the motion. And we can apply these same types of spreadsheet data reads and expression statements to things such as motors, actuators, as well as forces. So let's go ahead and select OK. So that's 360 degrees per second. And if we take a look at the simulation time, we'll be simulating for 1 second and 50 frames by default. I wish to capture a few cycles of this, so I'm going to go ahead and change this to 3 seconds and perhaps 600 frames. The number of frames here is going to help control the resolution of the playback of the animation. It'll also control the number of data points that are used to create the plots. With that done, I'll go ahead and click the Simulate button. And remember, it's simulating with true contact between the roller and the block right here. Okay, and it looks here like I might have a potential interference problem, so I'll use the interference tool to check that. After the simulation is complete, I can click and drag this, and now I'm not solving the math. Solving the math has already been done. Now I'm just replaying the animation. Okay, we suspected some interference between these two parts here. Let's go ahead and check that. I can come into the interference check tool, and a nice feature we have in here is to find the first contact to tell me if I have any interference at all. So I'll select the first contact, and then I'll come back here and I'll pick the two parts that I wish to check and choose Find Now. And sure enough, I immediately find an interference and it highlights those parts. So let's go ahead and let's make a design change so that we remove that interference. And because Dynamic Designer is embedded, there's really a seamless integration between the two. So I'll go ahead and I'll double click this link right here. And that activates the dimensions, and I'll go ahead and click on this dimension and I'll change it to something like maybe 46 millimeters. Okay, and there we have the updated model. You can see that it moved it to a new spot here. So if we go ahead and we reassess the calculation for the interference, pick the two parts, and did I grab the right part there? I think I did. Yes, I did. Let's choose Find Now, and it's not finding any interference. Okay. So we'll delete those simulation results. The next thing we'll do is we'll take a look at some of the information that's coming out. So now we've built this model, and now we can start reaping the benefits of extracting information that we were seeking. So one thing we wanted to look at was the torque required on this motor right here. And before I do that, let's go ahead and let's apply a force on top of this slide representing some sort of a load attached to it. So I'll click on the slide and I'll give it a location. I'll just select this edge here and a direction, and I'll select the face. And notice how it's going in the wrong direction there, so I can just flip this toggle. Now that force is acting downward. And I'll go ahead and say that it's got some load on it, maybe 5 pounds of force. Okay. And another thing I can do is I can turn off the animation while it's solving. So if I'm doing successive runs, making a lot of changes to it and rerunning it several times, I can turn the animation off so it only crunches the math. I still have access to the animation after it's finished, but watch down here when I simulate how quickly the slider bar will move across. There, I've just completed 3 seconds of data, but I still have access to my animation. So it just doesn't show the animation initially. My goal was to take a look at the torque required on this motor. I can right click on that joint now and plot, and notice how these different things are available that I can plot from. So whenever I have a motor or a motion applied to a joint, I'll have this motion generator option. And I'll take a look at the torque, and there we've got the torque profile. I've got a little bit of noise in the data. I'm not concerned about that at all. It's strictly, I've got a nice trend in the data. I'll certainly review it and make sure that it's nothing affecting the true performance of it. But I've got a nice clear trend. It's probably just some minor numerical error that I can easily fine-tune by modifying some simulation parameters. Okay, so let's go ahead and delete these simulation results. Actually, before I do that, let's take a look at these bearing reaction loads. That's something else we wanted to do. So we can click on this shaft, for example, and then we can right-click on the part here, and we've got this Add Result Object option. This allows us to create those vectors that I mentioned previously. So we can add some reaction force vectors on the shaft here. You can see these arrows that protruded from the shaft. Let's go ahead and let's change the color of those so we can see them better. I'll just come into my display settings, change them maybe to a dark blue, and now we can see those better. And I have a yellow arrow here representing a torsional moment on that joint. And now as I play this, I can see the reaction loads visually using those vectors. And if I want to see the numerical values of those, perhaps in graphical form, I can come down to the reaction force node here, and I can pick on my force inline and 0.127. Those are the two constraints. You can see them highlight in green. And then I can just click, hold, and drag and drop onto the XY plots node, and I'll plot the magnitude for those. So it's very easy to create these plots. And by the way, let's go ahead and delete these results. I'm going to try and fine-tune and smooth out the data a little bit. I'm going to use a solver that's more conducive for contact type problems, and I have a contact between that roller and that block, and I'll decrease the maximum time step as well. Okay, and it did I've got a little bit of a spike at the beginning here. Let's go ahead and let's delete these again, but you can see what it did and how it smoothed out the data on those. Let's just recreate the plots. Drag and drop. Okay, so a bit of a spike at the beginning right there. That's simply the model settling into equilibrium, but I smoothed out the data quite a bit here. So I can fix that by just double-clicking here, and I can change the scale to something like 10. There we go. Let's do the same for this one. Okay, that one was quite a bit lower, so change it to maybe 2. And the loads are pretty small on here right now. But I can do other things like add friction on these joints. And let's take a look at that. If I was to add friction on this sliding joint right here, how might that affect the torque on this motor? And so there's my motor plot right there. And what I'm going to do is I am going to preserve that data so that I can make a design change and then compare the results of the change to the old set of data. So here's the data for that meter. That's the moment on that inline joint. And I'll choose this preserve and copy option. And then what I'll do is maybe change the color of this curve. I like to use blue. We'll change that as the original. Okay, and we'll reset the simulation and delete the results. Now I'll go ahead and I'll add some friction on this sliding joint right here. So I'll right-click on that joint name, open the properties, and then I'll click on friction. Notice how friction is off by default. Again, I emphasize that crawl, walk, run approach. Start simple, make sure you've got the basics of your mechanism moving, and then apply more complexity as you move on. So we'll specify a value of 6, and then we'll specify a width of maybe 0.25 inches, and then a height of 1.5 inches. Dynamic Designer doesn't know the geometry exactly of the what we're applying the joint to, so that's why we specify it here. And now we'll go ahead and we'll run the simulation again. You can see that it hesitates now. It's because friction is a more intensive calculation. And there we have our results. You know what I'm going to do? I'm going to also change the type of integrator that we're using for this. Okay. And that gives it, and the reason we're not seeing this is because I've adjusted these scales manually. It's easy enough to recreate these, so let's select those two and delete them. And then we'll click on those forces and drag and drop onto the XY plots. There we go. So now we're seeing the effect of friction. And in particular, if we look at the plot for the motor here, we can see that friction added quite a bit to the torque requirement on that motor. We can plot the force for friction itself. If we right-click on the joint, there is now an option for friction force, and we'll plot the Z component. So we can see how much force was contributed due to friction. So I'm going to go ahead now and I'm going to close motion, and I'm going to proceed with showing you how we would prepare and transfer loads for a solid edge simulation FEA. So if we right click on the solid edge simulation here, I can choose new study. In ST9, this inertia relief feature has been added strictly for interfacing with Dynamic Designer. We'll choose OK, and then we'll choose the body to be included in the FEA, and I chose that arm there. So now that that's done, you can see we have a study defined with just a part. We'll proceed back to Dynamic Designer. Okay, and I need to delete the results and then simply rerun it again to refresh the fact that I now have a part included in here for the FE study. Okay, so if I look under Static Study 1, I have that component shown. And the next thing I need to do is I need to transfer the loads for that part. So this is up to the user to define at which point they'd like to transfer the loads. And you can also, by the way, transfer loads for one or more parts. You're not bound to a single part here. So what I might do is I might just move it to a suspicious point of high forces, for example. I'll take a look at, I'll just move it to maybe right there. And if I'm not sure, maybe what would be better is if I remove the plots that I have and actually created the plots for the constraints associated with that part. Those would be these three constraints right here. So I can come down here and I can pick on this 0.3216 and the revolute and revolute 2, and I can click, hold, drag and drop onto the XY plots, plot the reaction force magnitude. So now I'm looking at all the forces on that. What I might also want to do is create force vectors. This is useful from a visual standpoint, and I'll go ahead and I'll add the result object reaction forces. Now you can see those vectors coming out of that. And what I like to do is then just show that part. So if I show only here, I'm just looking at that part. And as I drag this, I still have all those graphics and everything showing. So it's a great way to sort of see a free body diagram snapshot of the load state of that part. And if I look here on my graphs, by the way, I can click on these graphs and move the cursor and the simulation to a particular point that I'm interested in. And I'll move it to that point right there. The next thing I'll do is I'll come down to the bottom of the browser here and I'll right click on that part and choose Add Loads. And when this message comes up, it simply wants us to define the load-bearing faces for the FEA. Dynamic Designer understands that there are constraints connecting bodies together, but it doesn't necessarily understand the geometric arrangement of those constraints. So for example, it'll calculate the loads for this pivot joint right here, but it doesn't know necessarily that those loads are distributed onto both of these holes right here. So we go in and we manually define those two faces. Let's come down here and we'll pick the bottom faces for this other revolute joint. And then we have this point constraint here finally. And now that I've done that, I can choose OK. And immediately you can see we have load representations of those forces. So if we close motion and enter solid edge simulation and expand the loads, we can see we have all the loads that were automatically set on the part. If we desire to look at a different load state, we can go back to Dynamic Designer. We don't need to delete the results. We can move the simulation to a different point, perhaps right there, and then we can transfer the loads again, and this time we don't need to define the load faces because they've already been defined. And you'll notice the loads have changed direction. So that's how easy it is to set up a motion simulation, extract good engineering data from this, and then transfer these loads as an FEA boundary condition setup to solid edge simulation. That concludes this demonstration.